In this video, we're going to talk about adversarial search and how to prune adversarial search algorithms to make them more efficient. So the plan is going to be we're going to briefly review what we've studied so far to help give us some context as to what we're looking at here. Then I'll talk about what's called the Minimax algorithm, which is the basic strategy we're going to take for the problem of adversarial search. And so as I'll also introduce the formalisms for how we describe this problem and how we're going to use it to model games. And then after we show you the basic, after we go over the basic algorithm, we're going to then look at strategies for how to prune the algorithm or prune the search space of the algorithm to prevent it from becoming too expensive. So previously we've been looking at non-adversarial search. So this is where we have a state space and we're free to explore it as our search algorithm, without this notion of an adversary or without any sort of hindrances to our ability to expand the states that we're interested in exploring. And basically all of the algorithms we considered for search boil down to a strategy for ordering the frontier, or ordering, among the nodes that you haven't yet expanded yet, that you are aware of, which one do you look at next? And as part of this strategy, we talked about heuristics, which are part of A star search, or more generally could be a part of any sort of heuristic-based search algorithm. But if you're using heuristics, pretty much you want to use A star. And we talked about characteristics of heuristics that lead to different aspects of search algorithms, which are the completeness aspect, whether a search algorithm is optimal, its time complexity, and space complexity. So it's a good idea at this point to take a pause and think about from a high level what about the types of search algorithms that we've considered so far and the search framework that we considered so far is lacking. And one of the things, there's a bunch of things, but one of the things that's lacking about this current search framework that we've been studying for the past couple weeks or week or so is that all we have is this single search agent exploring the space, and when you go to try to make a move, you just get to make that move. And in real world settings, or at least in slightly more challenging synthetic settings, you often have situations where there's something else working against you, whether it be the environment or another agent. And a good framework to think about these things is games, right? So a lot of games have this adversarial aspect where you make a move and then some adversary makes a counter move. So tic-tac-toe is a great example of this. And so what we're going to talk about for the next couple of classes and a few lectures is a special type of game. In particular, we're going to talk about zero-sum games of perfect information, and we'll also discuss how to move away from these settings. But for now, let's think about what this is. So a zero-sum game is one where when you play against an opponent, and when you win something, the opponent loses, and when the opponent wins something, you lose. So there's no way for us to cooperate. So there's no way for us to both win, or for you and your opponent to both win. But instead, you sort of play against each other. And it's called zero sum because obviously, because if you think about it, the person who runs the game doesn't have to pay anything unless they're taking a cut of the winnings. But in general, it's zero sum. The zero sum concept is basically that you could run the game for free. You just run it, and then if I win the game, I take money from my opponent, and the person who's the casino or whoever's running the game doesn't have to shell out any money. Okay, and so the way we're going to formalize this is we're going to have two players, and we can again we'll talk about how to move out of this paradigm at some point. We'll have two players. One of them we'll refer to as the max player, and the other one we'll refer to as the min player. And we're going to say this because we're going to name these players these names because we can, in the zero sum format, we can imagine that that one player is trying to maximize some value and the other player is trying to minimize some value. And you can always negate that and switch it around. So the second player is trying to maximize and the first player is trying to minimize. But it's easy to think about at the decision time. You could just imagine that the decision maker is always the max player, and the max player is trying to maximize his or her reward, while the min player is the opponent trying to minimize the reward that's going to be given to the current decision maker. Okay, and then I also forgot to mention on top that we're going to consider games that have perfect information. Now that means that there's nothing hidden. We're not going to be so. An example of a game that does not have perfect information is poker. Um, not only is there noise, is there randomness in poker, but players hide, what cards they're showing. Or, well, if you're familiar with poker, there's some versions of the game where you do have, in some sense, perfect information, modulo the randomness. Um, but an example of a game that has perfect information is like chess or checkers or any of these board games where you can see the entire board, you can see any information or cards or secret pieces that the other player might have that's fully visible to you. Okay, and as a result, you don't have to try to infer or guess any of these unknown bits of information. You just sort of make decisions based on fully observing the environment. Okay, and we're going to consider games where players alternate actions. In other words, players take turns looking at the current state and choosing an action that will cause a state space transition, just like in our previous search framework. But instead of a search algorithm choosing the actions, now players alternate choosing actions. Okay, and we can formalize this a bit further by thinking about the different components that we're going to need to describe algorithms or strategies for this type of setup. So what we're going to have is we're going to just define essentially some methods in pseudocode. All right, so the first is that will always be to take any state and pass it into some function player that tells us which player's turn it is right now. So which player gets to choose the action in state S. Okay, and then we can then also pass that state into an actions method that returns a set of actions that are available from state S. Right, this is just simple stuff to make the pseudocode work at a higher level. Okay, so now just like in the traditional search framework, we'll also have a transition model that's going to come from this result method that tells you what the result of action A in state S is, right? So it will tell us what state we end up in when we take the action from state S. Okay, now here's where things get a little bit different from what we've seen before. We'll have a terminal test. So this is a kind of a concept that's new to games. So in most games, and in the games that we're going to consider in this framework, there's going to be conditions where the game stops. Situations where the game is over and you score, you reward the players for how well they did. In some cases they just get a win or lose, or in some cases they might get some amount of rewards, or in some German style games you might hear about victory points, or in betting games you get some monetary reward or penalty at the end of the game. But the point is, there are situations where the game stops and scoring happens. And so the terminal test is just going to be a Boolean function that tells you, is this state a terminal state? Is this state a state where it's time to score the function, to score the game result, and then essentially either start over or just end the game. The game's over. And then finally, we have a utility function that takes in a state and a player and tells you the value of the state for the player P. So we're going to we're going to talk about algorithms and strategies for playing games with these abstract terms, and you can sort of fill in some concrete examples for these things. I mean, sometimes player S is just, if it's a really back and forth game like tic tac toe or checkers or chess, then player S just checks whether the state is essentially even or odd, right? In some sense, right? Every other move, it's going to be the other person's turn. And then the actions, we all know how to play at least one of these games probably. So you probably are familiar with what the actions are. Basically, we'll only consider the legal moves on the board, and the result is um, that's obvious. It's just a way of coding for a computer what happens when you make these moves. Um, and in a determinal test for say for example for tic-tac-toe would be are there three symbols in a row, or are there no more moves left on the board. And then utility for many games is just +1 or -1, or plus some number or minus some number if it's just a win or lose. Or if there's betting or money involved, then it could be you get payout for winning or losing the bet. Okay, so what we're going to talk about now is the famous strategy called the Minimax strategy, and we'll talk about how we implement it in a computer. But it's also good to just think about it. Forget about implementation. Let's just think about what is the strategy behind Minimax. The idea is that you're going to try to choose the move, assuming that the opponent plays optimally. Um, Moreover, you're going to assume that you're going to continue to play optimally, even if the player plays optimally. Right? So this is one of those things where that some people do um, when they learn chess, uh, and you basically say, okay, well, if I make this move, what's the other person going to do? And what's the best move for the other person, for the opponent? Um, given the move that I made, and then you think about, okay, well, now if they do that, then what am I going to do? It gets very confusing, of course, for a human to do that. So people have other ways of learning and memorizing good strategies in these complex games. But that's the general idea. And so here's how you would implement it, or one way to implement it in a computer. So this is a pseudocode for a recursive function that just computes the minimax score for any state. Um, and it's let me just walk through it. It's a little bit different than what's in the book, and I'm going to show you what's in the book in a minute. But let me just first show you this version. I think this version is slightly more robust to if the player turns are out of order. If it's not exactly it's not exactly that the min player goes and the max player goes and the min player goes. It could be different depending on the game, and this type of code would be more robust to that. Okay, so first, this function call, takes in a state, and the goal, I didn't write it out, but it's going to return a score value. It's going to return a numerical score for this state. And the first thing it does is it checks if this is a terminal state, right? If the game is over in state S, then just return the utility of state S. Okay, then it goes into a case statement. Basically, it just says whose turn is it, right? Is it player? Excuse me. Is it the max player's turn, or is it the min player's turn? Okay, if it's the max player's turn, then what it returns is the max of minimax um, of the resulting state for any of the actions that are available in the current state, right? So another way of describing this is that we're going to now try all of the actions that are available to us as the max player, and we're going to return the minimax score, computed recursively, of the resulting state if we were to try that action. Okay, and then similarly, the min player, if it's the min player's turn, it's going to do the opposite. It's going to return the minimum score of the minimax scores of all of its possible resulting um, states. So let's look at this. Let's try to visualize this. So this is a diagram from the book of a state space tree. So the idea is you can see at the top it's the max player's turn to choose where to move from state A. right? And then it has to move once it chooses a state to move to from state A, the min player then gets to choose how to move from either B, C, or D, and then it terminates. The the nodes on the bottom are terminal nodes, and so they have utility scores notated on the bottom. So what Minimax looks like then is it's going to first try state A, or rather it will try A1. Okay, and when it does A1, when it tries A1, it's going to then look at state B, right? It's now considering state B, and it's going to call Minimax on state B. And so let's think about what happens recursively when when Minimax is called on state B. And what happens is then state B is going to try, or rather the Minimax method called on state B is going to then try B1, B2, and B3. And each time it calls that, each time it tries those, it's going to hit the terminal test. It's going to hit the base case of our recursion. And so it's going to return the utility score for the resulting states, which will be 3, 12, and 8. And because it's the min player's turn, because it's moving from state B as the min player, it's going to choose the minimum value of that, which is 3. Okay, so we get 3 at state B. So now we know the value of the minimax value of state B is 3. And then the same process repeats for action A2, which leads to state C. And again, the min player is going to move from there and choose choose the minimum of the utility values, which is 2. And then finally, we would go to D and choose the minimum value of the possible moves for min, and we get again 2. So at this point, we have the scores for all of the max players' moves, from A, right? So now we have, A has 3 moves, and its utility, its minimax scores for its 3 moves are 3, 2, and 2. Okay, so then it's gonna choose the maximum value of that, which is 3. Okay, so that gives us the minimax score of state A. And so this is the pseudocode from the book. So it's a little bit different, right? And the difference is that it uses helper functions for the max value and the min value searches. So whereas I just wrote, in very Englishy, very high level pseudocode, I just wrote that it picks the max of the actions available. Here we're gonna actually look at the for loop, or we're gonna it's notated using the for loop that would be necessary to implement to find the max. Okay, and you can see how it works, right? It starts at the top level. It just activates the helper functions for all of the possible actions from the current state, and it assumes that we're gonna always be playing as the min player. Oh, excuse me, as the max player. We're always playing as the max player. So we call all the the min value methods for on the resulting states from all of our current actions, and then min value, what that does is, each of these does the terminal test. If there's a base case, if it's a base case, if it is a terminal state, then it's just going to return the utility score of that state. And otherwise, it's going to iterate through each of the actions available and call the other player's method, the other player's search method on the resulting state. So it's pretty straightforward. It's just this is hard. It's hard coded here that it always goes back and forth between the min player and the max player, which makes sense for a lot of games, but it isn't always the case. So at this point, let's think about how expensive is it to run this minimax decision algorithm. It's recursive, and so that should right away give you some clue that it might not be the most efficient thing. I mean, one of the things about recursion you discover during your career as a computer scientist, most of you probably have discovered this already, is that it usually makes for beautiful descriptions of algorithms, but not the most efficient implementations. As a rule of thumb, sometimes it does make things efficient, but usually it comes at a cost. But in this case, it's recursive. Okay, so what does that mean? It's going to always expand all the children of all the possible resulting states from any given state. It's always going to then call recursively the minimax method on these resulting states. And then those resulting states have to also try all of the possible actions and call minimax or some form of the minimax, or either one of these helper functions um, to compute the minimax value of all of its children in this, in the state space tree. So the bottom line, if you think about it, if you look at this picture, is that your minimax is going to pretty much always explore every single possible state that you can reach from the current state. Okay, that is extremely expensive because, right, these things grow exponentially, right? If there's three possible moves for you, your opponent has three possible moves for every possible move you made. So it gets very expensive. So we need to find ways to make this cheaper. And so that's where we get to pruning. So let's think about, is there a way for us to reduce the amount of exploration we have to do? Let's walk through what happens when we run Minimax iteratively, or not iteratively, but in order. Like, we'll step through the algorithm. Okay, so pretend we're at this state. We're currently at the state where we have explored the entire subtree of the B state. So again, we already did this a few slides ago. So pretend we're trying to compute the minimax move for state A, for coming from state A for the max player, and we considered action A1. We did the minimax procedure, and we computed that 3 is the minimax score for B. Okay. Now we're going to continue. We're going to continue the algorithm, and the next step is then to try action A2, taking us to state C. And then from state C, we're going to now try action C1, taking us to this terminal node, which has score 2. So we now know that, C are sort of our temporary variable for choosing the minimum value of all the actions available from state C for the min player, right, is currently set to 2. Okay, now we continue, and then we see another terminal state by taking action C2, and we see that it has score 4. And then at this point, we don't actually update our temporary variable because 2 is the lowest value we've seen so far, and 4 is higher than that. 4 is a greater number than 2. Okay, and then similarly, we see C3, and we get utility value 6, and we see that's greater than 2. So 2 is our value. Okay, so let's think about what just happened, right? So we saw 2, in the first step, and there's actually a clue. There's actually a way for us to tell that we should stop after that. And why is that? That's because, remember what our goal is, right? At the top level, at the very top level, we're trying to solve find the maximum scoring minimax move for the max player. Okay, and so you can even imagine, even in some scenario where we change the scores, instead of having 4 and 6 as the next two states coming from C, we could put them even lower. They could be lower than 2. They could be 1 and 1. So now, if we really wanted to find the minimum value, the minimum scoring state from C, we would have to at least consider C2. But if you think about it, once we've seen 2, once we've seen the action C1 to the state that gives us a utility score of 2, we already know that A1 is a better action for the max player than A2. Right, so the reason is, again, the max player is trying to pick a minimax value that is as high as possible. And action A1, we've already figured out by exploring the entire subtree of B, that action A1 will give us a minimax score of 3. And then action 2, we discover that there's a way for the min player to score 2, to make the utility value 2. It doesn't matter that the player can also make it 1. The min player can make it even worse for us, but already, because the min player can make it 2, it's a worse move than A1. A2 is a worse move than A1. So for the sake of making this example work a little bit better, I'm just going to reverse the order of the moves from D. So if we look at the third branch and we consider that the nodes have been reversed, again, we have the same situation. We see that from D, the min player can make a move that gives us a utility score of 2. And so in the same way as things are progress from state C, it doesn't matter what the other moves are available to min, right? Because we already know that min can make a move that makes the branch, that the result of the game that happens after state D, worse for the max player, worse for us. We're the decision maker as the max player. Worse for us than if we were to take A1. Okay. And so this is the basic intuition behind alpha beta pruning. But the key is that alpha beta pruning is a little bit different. What we just did was just sort of walk through the thought experiment if we're the max player and we're trying to prune. But alpha beta pruning is trying to prune both as the max player and as the min player. And it becomes important in deeper trees, right? Here we only had a 3-level tree. And so what it does to handle both the min and the max pruning is that it's going to keep track of 2 numbers for every single node. It's going to keep track of the alpha, which is the highest value choice along the path, and beta, which is the lowest value choice along the path. And then the whole strategy is built around comparing the alpha and beta values of different nodes and different subtrees to decide whether we need to continue searching any particular subtree. So let's go through the example that's in the figure from the book that I copied here onto this slide. So it starts out with, it's the same tree that we looked at before, but the important thing is now we're going to look at, how we implement it with this upper and lower bound, the alpha and the beta. So when you start out, the root node has an alpha and beta of minus infinity and plus infinity because we haven't seen anything, so we can't say anything about these are like the worst case, right? So remember the first term is supposed to be the highest value node that we've seen on the path, and the second term is the lowest value. And right now we set them to infinity as basically sentinel values. So when we look at state B, we see that has a alpha value of minus infinity still, but it has a beta value of 3. Now what does that mean? It means that is so far that is the lowest scoring node that it's seen along its path. Or rather, it's the lowest node or lowest value node that uses B on its path up to the root. Okay, and then as we continue searching, we're going to look at the next sibling of that state that gives us score 3. So it's 12, and so that doesn't change our values, right? It doesn't change the 3 because 3 is smaller than 12, and then similarly 8 doesn't change the value. But what it does tell us now is that we've now explored the entire space of possible states that we can get to from state B, and now we can say that the highest value, the highest minimax value that we can get to from state B is also 3. In other words, right, when we see that the 3 is the alpha and the beta value, we've actually found the exact minimax value, right? And so this should give you a clue as to what these alpha and beta values are, right? Because they're upper and lower bounds. And if you think back to where we were before, we initialized them to be minus infinity and plus infinity, which basically translates to, all we know so far is that the minimax value for this state is something in between minus infinity and plus infinity, which is all all real numbers. So instead, as we start exploring, and in this case we've explored the entire subtree around underneath state B, we can get the exact minimax value, which is 3. So now we've sort of sandwiched with upper and lower bounds of the exact same value. And because we now know the minimax value for state B, we can propagate that up and think about, what do we now know about these alpha and beta bounds for state A? Okay, and what we know is that we've seen a state that has minimax value of 3. So the lower bound has to be at least 3. Right? If we find another state that's better than 3, then it'll increase that lower bound. But for now, we've seen at least we can get score 3 if we choose state B, right? If we choose the move that takes us to B. So far it's not all that interesting, but then things get interesting when we start looking at other branches. So now when we start looking at state C, we look at one of C's possible children, and we immediately know that the min player's upper bound is 2, meaning that the min player has at least an option as good as 2. Now it might be to get an even better option if they can find an even lower value than 2. But just like we talked about in the last example, which is the same example without the lower and upper bounds, we already know something here, right? Because the min player can score 2, which means that the upper bound, the maximum possible minimax score that you can get to by choosing a move that takes you to state C, is 2. And we already know that we have a move better than 2, right? As the max player, we have a move that's better than 2, that's bounded, or rather, the lower bound for the move that we're considering is already lower than our upper bound for the minimax score of A, which means we no longer need to consider searching this subtree, because that gap can only widen, right? We've already found that the current state we were considering, or the current path that we've considered, that we've seen so far as we look down the path going through C, is already telling us that this score is too low. This score is too low for us to consider. And when we continue looking, we're going to find even lower scores, or we'll find the same score, but it can only get lower. So we can immediately prune this away, or rather, we can just move on from this branch. We don't need to consider it anymore. So instead, we can move on to what happens if we go to state D. So the first thing that happens when we go to state D is we see that there's a possible utility score of 14. Okay, and that means that D's upper bound is now 14, right? There's no way that the min player, now that there's at least one score of 14, the min player can only choose a move that's going to be better than 14. Okay, and then that also propagates up, because that means that as the max player, you can sort of see that this looks like really good news, because now all of a sudden there's this option that based on just the tree that's on the screen right now, pretend you don't remember what the tree looked like before we sort of hid some parts of it. It looks like there's a move that might get us as the max player a score of 14, which is way bigger than what we thought before. Right? We thought the best move we had was 3. Or had a utility value of 3. And now we see that if we go to D, if we take the move that takes us to D, the min player has a move that's going to give us a score, or give the total score of 14. Okay, but then the diagram skips ahead in the book for the same reason that I sort of reversed the order of those nodes, and you'll see that eventually, once you expand or explore all the nodes of D, you discover that D has a minimax, lower and upper bound of 2 and 2, meaning its minimax value is exactly 2. And the algorithm wouldn't discover this until it finds that node down there that's 2. And so you can imagine if you ran the whole algorithm, step by step, what would happen is the max score, the max player would sort of see, be very hopeful, when you see the score 14, that okay, maybe there's some lucky way that 14 is the value we're going to get. And then you check out the next node when you get a score of 5, and that lowers this upper bound, and the max player now says, okay, well maybe we'll get 5, and similarly the min player thinks that maybe 5 is the best that we can get, and finally you see the 2, and we've explored the entire subtree underneath D, and we know the exact minimax value of D. So this is the whole diagram. You can see the steps of the algorithm, and looking at this diagram, it's not completely obvious, at least to me, how to implement this. Now, it's straightforward once you have somebody write out the pseudocode for you, which the textbook has done for all of us. But if you just look at this diagram, things get a little bit hard to keep in your head. Right? We've managed to keep track of the, we keep track of the numbers, the alpha and beta numbers, but then where the decision points are for when you compare them and when you decide whether to prune away or ignore the rest of a tree is a little bit tricky, or at least to me it is. So we can stare at this image for a bit and try to think about where we should be checking the upper and lower bounds, and what are the pairs of states we should be checking. And one intuition is that we should definitely be checking something, one of our ancestors, right? Either the parent or something that is above us in the tree along the path to the current state. And we sort of have this intuition, which turns out to be incorrect, that what we should be doing is we should be comparing one move to another move, right? That's sort of what we did when we sort of did the example out and just sort of drew it on the screen. But it turns out that that's not the best way to do things, or at least it makes things more complicated than they need to be. Instead, by this whole concept of storing the alpha and beta, bound upper and lower bounds at each node, we don't have to go back and look at alternate moves or look at previous moves that we've already considered. So, for example, if you look at subfigure D in this slide, this was the key scenario. This was the situation where we are exploring possible moves for the min player from state C, and we've already previously looked at all of the details, all of the possible moves for if we go to state B. And intuitively, again, it sounds like we're comparing a move to C to a move to B, and we're kind of doing that, but it's very implicit, because all we have to do instead is compare the move to C to whatever is stored at the parent A. Okay, and this is how the pseudocode works. So it's very similar to the code I showed you before for Minimax search. Again, we're using this is looking at the book pseudocode, which explicitly separates out the max method and the min method. But in this particular case, it actually makes things more convenient than if they were sort of jammed into one single method, just because we treat the alpha and the beta values differently depending on if you're the min or the max. So the key line of code you should look at is what I've highlighted in blue, which is, let's just look at the max value method for now. It says that if v, which is sort of this, okay, so backing up, v is the temporary variable that we're using to hold the maximum value seen so far as we explore the possible moves from this state. So if v, the temporary variable, is greater than beta, then we return v and just stop the search. We don't continue looking at the other possible moves that we haven't yet explored. So looking back up, what is beta? Well, beta is going to be the lowest value that the parent has seen so far. And what this means is that, in the middle of, or probably before, all the actions have been explored, we've already seen a, max player move that is better than the minimax, or the sort of the bound on the best minimax move for the parent, which in this case would be a min player. And so the reverse logic occurs in the min value method. And then, the other thing to keep in mind is how we update these values. So after we discover a value that is greater than, for example, our lower bound, then we would update our alpha value. And similarly, if we discover a value that's less than our upper bound, then we will update our beta value down below. So that's the pseudocode, and it's a kind of a simple idea, but it's pretty hard to get things flipped. There's a lot of upper and lower bounds. There's signs of what you want to be greater than or less than other pieces of the the data that we're storing. It's pretty easy to get tripped up with this stuff. So I admit that I'm getting a little confused going through this myself. Usually you can see right away by running through a couple of examples whether you have one of these inequalities flipped. But it's like I said, it takes a little bit of work. So we'll go over this in class. We'll talk more about how this can be implemented, and go through some examples maybe if that's going to be helpful for you. And then we'll also talk about some other things. So there's a few things that are in the textbook, a few concepts that are interesting to think about. So one is a transposition table. So the concept of sort of having a cache of previously seen states and looking up in the cache before you go and compute minimax. Maybe you've already computed the minimax value for that state already, so you can look it up and it saves a lot of time. That's the situation where it goes a step in a different direction than alpha beta pruning to make things faster. And you can imagine how this can be really important, especially in games where there's an infinite search space. Like you can imagine in chess where you have moves, players or pieces that can move back and forth. They don't have to be, they're not like pawns where they can only move forward, but they can move in multiple directions. Like queens. You can have you can have repeat states all the time, right? So when we think about doing a search to find a terminal state, there's going to be paths that go on infinitely. Assuming you don't have, like a draw rule, like in chess. And so, having a cache can prevent you from, recomputing the minimax value for a state you've already seen before. Okay, and then similarly, another way to handle situations with very deep search trees or with infinite search trees is to have maximum depth heuristics. So you basically say, I'm going to run minimax, but I'm going to keep track of how deep I've been searching in the tree. And once I reach some maximum depth, maybe it's determined by how much memory we have, or maybe it's determined by some time limit. We're just going to run some heuristic on the current board state or the current game state, and try to determine the scoring, the scoring payoff, the utility value based on a heuristic, based on a guess. And so this is where, in the first class we talked about how we could come up with a performance metric for chess. And one of the performance metrics is these, again, heuristics, where the real bottom line is whether you checkmate the opponent's king or not. But along the way, you have heuristics like the value of the pieces on the board, the amount of space you control, the amount of tempo you have. And that's where these heuristics can come into play. So the material that this video covers lives in Chapter 5 of the textbook, in particular the beginning of Chapter 5 up to the end of Section 5.3. And for class, I'd like you also to read 5.4, which is a section that deals with the some variants of some of the things that we talked about in this video. And then we'll talk about all these things, we'll go over some examples, and try to answer your questions in class.